is not an empty set because there is some positive power in there. I'm going to take the smallest one. And what I'm going to do now is show that H is actually generated by A to the M. I want to show that H is cyclic, so I've got to show it's generated by something. I'm going to show it's generated by A to the M. Well, I'm showing that two sets are equal now, and the way I'm going to do that is the usual way, in fact, for showing that each is a subset of the other. Well, the right-hand one is certainly a subset of H, because remember, A to the M is in H, so all powers of A to the M are in H, because H is a subgroup. So A to the M is in H, so all powers of A to the M are in H, because if I multiply any two elements of H together, I get something in H. If I take inverses, I stay in H. So that since H is a subgroup, so it remains to show the other way, that H is a subset of A to the pointed brackets A to the M, and then we'll have equality. So let H be in H. What I want to do is show that every element of big H is also in pointed brackets A to the M. So I'm going to take a typical element of big H, call it little h, and I want to show that little h is in pointed brackets A to the M. Well, little h is in big H, but every element of H is some power of A, because every element of the whole group is some power of A. So I'm going to write A as, say, try and use some different letters, say T. Okay? Every element of the big group G is a power of A, so little h is certainly a power of A. So I'll call it A to the T. Well, now I'm going to use the division algorithm again. I'm going to write T in terms of M. So I'm going to call it, say, QM plus R, where Q and R are integers, the quotient and the remainder, because I'm dividing by M, notice, the remainder is between 0 and M, possibly 0, but not M. So I'm using the division algorithm again there. I'm dividing T by M, because I'm interested in M now. So then I get H is A to the QM plus R, because T is QM plus R and H was A to the T. Now I'm going to use my index laws. Notice I'm using the index laws all the time. So this is A to the M, all to the Q, A to the R. I've used index laws. I've used two different index laws there, but that should be okay. So I've first written this as A to the QM, A to the R, and then I said that A to the QM is A to the M, all to the Q. So that's using index laws. Both kinds of index laws, in fact. Is that okay? So remember, the index laws are what you've been using for years, so there's no sort of voodoo going on there. It's just the index laws you've been using for years. Now, what I'm going to do now is rearrange this. I want to get all... I know that some of these elements are in H. So little h is in big H. And this is in big H because it's the power of a to the m. So let me just write this down again. And that's just what I had in the previous page. I'm just going to rearrange this. Oops, A. Sorry. Start again. A to the R is, I'm going to get A to the R on its own. So I'm going to pre-multiply by the inverse of this. Now I've done a couple of steps at once there. I've pre-multiplied by the inverse of a to the m to the q, which is a to the m to the minus q. So that gives you a to the m to the minus q times h, and then I'll have a to the r left on its own. So I've done a couple of lines there, but so what do I have on the right hand side? Well, little h is in big H. A to the m, remember, is in H, because remember what m was. M is the smallest positive integer, such that a to the m is in H. So a to the m is in H. And then we've got some power of a to the m. But H is a group, so any power of an element of H is also in H. So then I've got something in H times something in H. This is not very elegant, but the result is that the right-hand side is in H. So what we've got is that a to the r is in H. But remember what r is. It's the remainder on division by m. So it's somewhere between 0 and m, possibly 0, but not m. If r wasn't 0, can you see what we'd be saying here? If r wasn't 0, we'd have a positive power of a being in H. And that positive power would be less than m. But m is the smallest positive power. So since m is the smallest positive power of a that lives in H, we must have r equals 0. Because otherwise r would be a positive number smaller than m, such that a to the r was in H. But m is the smallest one. So r's got to be 0. So, just going back to here, r must be 0, so t must be qm. Which is a to the m all to the q. So what we've proved is that our element little h is actually a power of a to the m. So in other words, H is in the subgroup generated by a to the m because it's a to the m to some power. And that concludes our second part of the proof, that H is indeed a subset of a to the m. Everything in H can be written as a power of a to the m. Remember, that's what we're trying to prove in the second part. It's the end of the proof. So that's written out in full. Again, I'm not expecting you to follow it all just watching it whiz before your eyes now, but you can watch the video again. You can look at the proof in the notes or in the lecture notes or in Fraley. But the proof is understandable, but probably not done so fast. So what we've just proved, and sometimes at the end of a long proof you do have to remind yourself what you've just proved, we've proved that if you've got a subgroup of a cyclic group, then it's also cyclic. Okay? And now we can put all together several of the ingredients that we've had this morning into one big package. And this is sometimes called the fundamental theorem of cyclic groups. And I won't prove it now because I think I want to try and do an example before the end. You might want to call it the fundamental theorem of cyclic subgroups, but different people call it slightly different things. And some people would include the result that we've just done, that every subgroup of a cyclic group is cyclic. They would include that in here. But I will just state it as follows. So let G be a cyclic group. I'll actually need that G is finite now. Let G be a finite cyclic group. Then there is a one-to-one correspondence, in other words a bijection, between two sets. One of them is a kind of group theoretic set and the other is a number theoretic set. So between the set of all positive divisors of the order of G, which is some positive number, positive integer. So it's a one-to-one correspondence between this set and the set of all subgroups of G. This is one way of saying it. So if you can count positive divisors, you can count subgroups. And in fact, the proof actually involves, or the way I would prove it, involves actually writing down an explicit bijection. So let's say the order of G is n. Remember, it's finite, so its order is some natural number. So I'm going to look at all the divisors of n. So imagine some positive integer n. So this is a set of all positive divisors of n. And then we've got the set of all subgroups of G. So this looks a bit formal. And remember that we know that every subgroup of G is cyclic. And I'm going to define a bijection from this set to the other set. So let's have a generator for G. Suppose G is generated by A. And we'll give this bijection a name. Let's say call it big phi. This is not standard notation, we'll just call it something. Big phi. So I'm going to take a divisor of n, and that's going to map to some subgroup. Well, there's two kind of obvious things to do, and one of them is actually a bit nicer than the other. Perhaps the most obvious thing is to say, well, look at a to the k and take the subgroup generated by a to the k, which would be okay, but it's actually slightly nicer to look at n over k so this looks a bit forbidding perhaps, but so let's just sit back and lean forward and look at what we've got here, and we'll do an example in a second. So we've got a function from the set of all positive divisors of n. So say n was 24, then this set would be 1, 2, 3, 4, 6, 8, 12 and 24. So that's a number theoretic object, just looking at divisors of n. This is all the subgroups of G in a bag. And to each divisor, we're going to give a subgroup. So we take this k, which is some positive divisor of n. So n over k is also a divisor of n. I look at a to that power and just take the subgroup generated by that. So this is certainly a subgroup of G, so it does live in here. And the claim is that this is actually a bijection. It's injective and surjective, so it gives us a one-to-one correspondence between these two sets. And to prove that it's a bijection, we need a couple of the results we've already proved this morning. So I'm not going to do that now. But for instance, to prove it's surjective, we take a subgroup of G. We know it's cyclic, so it must be generated by some power of A. But we can reduce the power to be a divisor of n by one of the results we proved. And then we use that divisor of n to extract k. And that will be a k that gives us any element here. So that shows it's surjective. And the way you prove it's injective is if you've got two different k's and they've got to go to different places, because the order of this is actually k by our formula. The order of this right-hand subgroup is actually k, because it's going to be n over k, which is k. So different k's go to different subgroups. That needs a few minutes of unpicking. Okay? So I'll just rather optimistically put the end of proof symbol there, because there's a few minutes worth of details to fill in. But let's just look at an example to finish off. Just one remark before I do an example. The order of any subgroup, since this is a bijection, in particular it's surjective, every subgroup has order a divisor of n. So in a cyclic group, if you take a subgroup, it's the order of the subgroup is a divisor of the order of the group. And in fact, that's a special case of an important theorem which we'll get to towards the end of the semester, called Lagrange's theorem. It's true for any finite group. But if you've got a finite group, you take a subgroup, the order of the subgroup will divide the order of the group. That's true for any finite group. We're seeing it here in the special case of finite cyclic groups. But it's actually true for all finite groups. For cyclic groups, we've got more. Every divisor gives us a subgroup. And that's not true in general. It's true actually for all abelian groups, but we won't get to that. Let's just do an example. Let's just take G to be, say, and I think this is possibly the example I did in one of the tutorials yesterday, but we now can do it in the knowledge that we've stated all the results clearly. Let's take the cyclic group of order 12, which, remember, there's only one of them essentially, so we'll use Z12 as the model. So that's generated, for instance, by the number 1. Now we're using additive notation, just the usual caveat. So to compute subgroups of Z12, so remember Z12 is 0, 1, 2 up to 11. That's the economic way of writing it. Integers modulo 12 under addition modulo 12. To compute the subgroups of Z12, all we need to do is look at the divisors of 12, which is the 12 being the order of Z12. So we just need to write down the divisors of 12. Make sure you don't miss any out. The positive divisors of 12 are precisely those 6 natural numbers. So what the theorem says, the fundamental theorem says, this set of 6 numbers is in bijective correspondence with the set of subgroups. And we can just write them down. So there's a subgroup generated by, well, again, we're using additive notation, so the powers become multiples. So it's just this slightly pesky jump from multiplicative to additive notation. So rather than a to the n over k, this would be n over k times a, and in fact a, our generator, is 1. So multiplicative notation becomes additive notation. And in fact we probably wouldn't tend to write the 1 in, although technically we should. So I'll be slightly sloppy and write this as n over k, 12 over 1, 12 over 2, 12 over 3, 12 over 4, 12 over 6, and 12 over 12. Those are all our subgroups of Z12, and they're all different. In fact, what are these? Subgroup generated by 12, subgroup generated by 6, subgroup generated by 4, subgroup generated by 3, subgroup generated by 2, and the subgroup generated by 1. Well, I don't want to squeeze them all here, so let me just, well, for instance, 12 is equal to 0 modulo 12, so the first one is actually the trivial subgroup, and the last one is actually the whole of Z12. So the way I've written it, using n over k rather than k, means that I get them in order going from smallest to the largest. So let's just do an example. What about the subgroup generated by 4? So that contains the identity. 4 plus 4 is 8, and that's it. And then the one generated by 6 contains 0 and 6. This was 0, 3, 6 and 9, and it's getting very squashed. This one has 0, 2, 4, 6, 8 and 10. So that's a bit squashed. So those are all the subgroups of Z12. They're all cyclic. Notice, by the way, so what about the subgroup, say, generated by 8? But that will be the same as the subgroup generated by 4. And that's because the greatest common divisor of 4 and 12 is the same as the greatest common divisor of 8 and 12 by a previous result. Okay, so the number theory is where we started with, and that gives us all the subgroups. So this is the power of this result. We reduce the issue of listing all the subgroups to one of listing all the divisors of a number, which in principle is a lot easier. Okay, and as we did in the tutorial, and as you will be doing in the worksheet for the coming week, not only can you write these subgroups down, but you can organise them into a nice lattice diagram which shows their interrelationship. And we can discuss that. We discussed it a little bit yesterday, but we'll discuss it more in the tutorial next week. Okay, so thanks very much for